This week we're going to talk about horizontal stakeout methods and offset stakes. Now there's two types of stakeout methods, primarily radial and baseline stakeout. Radial is by far the most common. It's become simplified in not recent years, probably the last couple decades, with electronic data collectors and total stations. The measurements are performed off of existing horizontal traverse points, and the real benefit to radial stakeout is that it's performed by one instrument location. So you're saving time, you're minimizing setup errors, and all of the types of random errors that are introduced when you set up an instrument over a control point. Baseline method, it's used primarily more on linear features or route features. You establish a reference line with respect to the design feature, and you're simply occupying points along that reference line and turning right angles to stake out either your feature or offsets to your feature. You can do this with buildings if they're not too complex of a foundation plan, but generally radial stakeout allows you to accomplish a lot more in a lot less time. Now if we look at an example of kind of radial stakeout, how this works, kind of showing three control points on a job site. Control point 1, 2, and 3, and there's probably more. 3 would be the minimum you would want for one level of redundancy. And we have a building location somewhere on that job site. The location of that building is kind of identified by coordinates, northings and eastings, with respect to the coordinate system that was established by our control points, from the traverse. And those building corner locations can be identified as individual points themselves. We'll just call them A, B, C, and D for now. And we would need to pick an instrument location where we would want to set up our total station to which we could see the stakeout points A, B, C, and D. So in this example, I'm going to show a setup down there at CP2 and a backsite up there at control point number 1. So that becomes our backsite reference line. And there's no magic reason it has to be 0, but that always makes the math easier if you're doing it by hand. A computer field calculator doesn't really care, but we still generally 0 set our backsite to eliminate potential errors that could be occurring from random numbers. So point A is going to have both an angle referenced off of that backsite and also a distance measured from CP2. And those are the two measurements, right, that a total station can give us. They can give us a horizontal angle and a slope distance with a zenith angle. Those two components together could help us compute the horizontal distance, which is what's required for stakeout. And that process is simply repeated for all of the individual points that need to be staked out on a job site. Point number B is going to have its own angle and its own distance. Point number C is going to have its corresponding angle and distance, and point number D. And all of these measurements are radiating out from control point 2, which is why we call it radial stakeout. It's really efficient. It does introduce the potential for error, so it's definitely imperative that you check the integrity of your stakeout. If this was the feature we were actually staking out, a rectangular foundation, we would definitely want to pull maybe diagonal distances, make sure they're equal. That generally indicates you have a square feature. We could also check that the walls are 90 using a couple different methods. 3, 4, 5 is the easiest method to do that, and your textbook talks about how to execute a 3, 4, 5 triangle with a tape measure to check the squareness of a building corner. So the radial stakeout calculations, I'm going to have you do a couple of these for homework this week. And we'll just talk about the process here to help you work through those calculations. This example comes straight from the textbook, Crawford, chapter 15, pages 27 and 28. And we're just going to look at the process of calculating the layout data for control point, or for stakeout point number 1, off of control points E, which is the instrument location, and A, which is the backsite location. And you can tell E is the instrument location because of the radial stakeout data being computed from it. So for the layout angle, the direction of your backsite, so the direction of this reference, the direction of this reference line, we're going to assign the angle 0 to it with regards to our instrument, but the direction is a function of the coordinates, or it's a result of the coordinate system that we've applied to that. So don't get the backsite angle confused with the backsite direction, because the book does kind of differentiate those for you. So the direction of your backsite is the inverse tangent of the difference in your easting coordinate values. So the easting of point E, which is your instrument, and the easting of point A, which is your backsite, divided by the difference of the northing coordinates of your control points. So the northing value of control point E and the northing value of control point A. You divide those two results and you take the inverse tangent, and that gives you an angle or a direction. And probably decimal degrees. Whenever you get a result in decimal degrees in your calculator, you certainly want to convert that into degrees, minutes, and seconds, because that's the format of an angle that we're going to assign to our tools when we measure them in the field. Similarly, for a foresight, the direction from control point E to, so from control point E to stakeout point number 1, again, it's the difference in the eastings, instrument location, minus the desired site, divided by the difference in the northing coordinate values, instrument location E minus stakeout point number 1. Those differences applied the inverse tangent to that result, and again, you'll get a direction of that line. The angle right that we need to turn, so the angle from our backsite line to the foresight line, is simply the direction of your foresight minus the direction of your backsite. So two bearings essentially, or two azimuths subtracted, give you a resultant angle, and that angle is the angle that we turn with our instrument. So the layout distance is a little more simple, and it's a formula that you're used to seeing, maybe just not in this form. But the distance of the foresight, so the distance from instrument location E to the point we're going to be locating, point number 1, is equal to the square root of the difference in your northing values squared plus the difference in your easting values squared. And if you kind of dissect this equation a little bit, you would see that it's just another expression of the Pythagorean theorem. C squared equals A squared plus B squared. C in a right angle triangle is always the length of the hypotenuse, and essentially that's what we're creating here, is a right angle between E and 1 and a perpendicular extension down to our backside, where this would be the right angle of our right triangle. So the difference in your northings is one side of your triangle. The difference in your eastings is another side of your triangle. And the distance that we want to solve for, the distance that we're shooting, is the hypotenuse of that right triangle. So a squared b squared c squared has some new terms applied to it. So the distance equals difference in northings and difference in eastings. I'm going to have you go through those calculations a little bit for homework just so you're familiar with where they come from. But nobody does this in the field in practice, and I'm not going to make you do it in the field in practice either. We're going to use electronic data collectors, which use the coordinates that we're going to upload into the job file, and they'll compute the angles and the distances that we need to lay out with our total stations to place that point in the ground where it needs to be. So this concept of offsets is important with horizontal layout as well. And if we look at, or if we think about that rectangular building location again with points A, B, C, and D, if we were to set points A, B, C, and D directly in their intended locations, the second an excavator comes through with the backhoe, those points are gone. So when control is gone, the contractor is lost, and what we provide on the ground has to stay there for an extended period of time to assist the contractor for however long of a period, a few days, maybe a few weeks, or even months. So we set offsets to the actual feature, and those offsets are generally in line or square or perpendicular to lines of those features. They could be both directions, and it's not uncommon for a four-sided simple rectangular figure to require 8 offset points. Offset points going each direction off of each corner. And from those offset points, you can then essentially connect extensions which create those wall lines or those design feature lines for the contractor. And that's done typically by the contractor with batter boards. And batter boards is not something we're going to build or construct in this class. It is in another class, but it's important to know, for you to know what a batter board is, because that's what your control, right? That's what your stakeout point is being used for. And a batter board is simply kind of a reference surface, a reference feature, such as a 2x4. Sometimes they're a little more durable, or if they're going to be lasting a long time. And then they pull strings, and they're pulling strings directly across your offset hub, which would be something like down here. These examples come directly from the textbook, and these pages are part of the reading I'm having you do this week. So these offsets, what distance do you set an offset from a feature? And this is kind of a trick question. It's whatever the contractor requests. When you're working out there on a construction site, especially as the construction surveyor providing these stakes, you're essentially working for the contractor. It doesn't matter what engineering company you're with, who your design engineer is. That day, that moment, when you're out there putting points in the ground, you have to provide the contractor what they need. So work with that contractor. Know ahead of time, before the job starts, what they're going to require. Do they want 5-foot offsets? Do they need 20-foot offsets? A lot of it depends on the stability of the soil. If they have to step those soil trenches back quite a ways, they're going to need longer offsets. If it's really stable soil and they can work with trench boxes maybe and dig some pretty vertical walls down for their foundations, maybe they can get away with shorter 5 or 10-foot offsets. But the answer is whatever the contractor wants. So always ask, don't ever assume. Some of the typical features then that we're staking out. Top back of curb is probably the most common. Everybody stakes out top back of curb at some point in their careers. And these are some examples of Some jobs, this one on the left here is Catlin Street in Missoula, and these other two are, I believe they're a Bozeman High School renovation project from a couple years ago. And curb and gutter, we're going to look specifically at curb and gutter later on this semester, so I'm not going to spend a whole lot of time talking about its geometry and how it's designed. But these hubs you see in the ground here in these photographs, these are the offset points to what is essentially going to be the top back of that curb and gutter once it's poured in concrete. And in Montana, every single contractor is used to getting a 3-foot offset. That's the way most of the equipment people use around here is configured. It's not going to surprise anybody. I've never seen anybody stake anything different than a 3-foot offset for top back of curb in Montana. And you can see in this middle picture here, there's quite a cluster of stakeout points. You've got a 3-foot offset to the point of curvature, a 3-foot offset to the middle of the curve, and a 3-foot offset to the end of the curve. And then you also have a middle point, which is the radius point. It looks like that's about 1 foot away, so I bet that's a 4-foot radius curve. This is the kind of stuff that drives surveyors nuts, because it takes 4 points to essentially create a tiny little curb bulb. This is a little different part of that parking lot in the right picture, but these are 3-foot offsets to the corner of that parking lot. And I just wanted to kind of break away from offsets just for a second here and talk about how curb and gutter is poured. Typically, it's done by setting string lines. So the contractors come through after you've set your offsets, and they set up these smooth bars, these like a 5/8 bar, and they set this string line either at a prescribed offset or directly over the location where the curb and gutter is going to be. It all depends on how their machine is configured. And these machines have a little sensor, a little arm, that rides right along this string, and that string is guiding the machine. And this curb and gutter, then the concrete gets spit out down here like toothpaste. And there's really no hand forming, there's no handwork unless you're on an intricate, tight curve. There might be some handwork done. But curb and gutter is really automated now. And these string lines are an expression of your stakes that you've set in the ground. Both location, which is the horizontal position, and grade, which is the vertical location. But that's kind of going away now. Stringless top back of curb is probably, well, it's not too common yet around Montana, but it's going to be because of the labor savings in that. And this was a demonstration in Belgrade back in the summer of 2017 that I went to go see from a company, Treasure State Incorporated. They do a lot of concrete work all over the state. And this is a stringless curb and gutter machine. It's all GPS driven. So you can see over here, there's a few control points that were established out here, and no strings. This entire curb and gutter was alignment was maintained through an RTK GPS right here. The grade, so the slope, the vertical component of this curb and gutter was maintained also by another sensor. I think it was either here or here. But there's a laser level on site that's helping this machine control the vertical location of the curb being placed. And GPS, RTK GPS, is controlling the horizontal location. It doesn't even need a string to go around curves. It's using a predetermined alignment, a digital alignment put in its computer to guide it around these curves. And it's an amazing technology. I think right now a lot of engineers probably don't trust it because they haven't seen it seen it in action quite a bit, and they want to know that it's going to deliver the same level of quality that hand forming and strings do. It certainly will. Um, I think it actually removes a couple degrees of error. You know, you have a lot less hubs to set, a lot less strings to set. Every time you put something in the ground, you're having to measure it. And whenever you measure, you introduce error. This eliminates a lot of measuring. So it's very expensive. They're really trying to market it and push it so they can justify it and help pay for it. And I see in the near future that we're not going to be setting strings anymore. So back to offsets. Offset distances. Remember top back of curb, that's 3-foot offset in Montana. I don't think you'll ever see anything different. Pipes, typically you're going to be asked to set offset points running parallel with the pipe, probably 10 feet off that pipe at least. Depends on the size, obviously, and the depth of the trench, but I would say 10 feet is a good number to remember. Manholes, and I think this is also true for water valves, any kind of fixture on a utility line in the street. Typically 10 feet. You can do it two different ways here, and I'm showing with the manhole. Our goal is to locate the position of the center of that manhole for the contractor. So it either has to be done with two offsets, equidistant, each 10 feet, so they can pull two distances and recreate that location. Or if two locations is inconvenient, you can pull one direction with two different distances, and 10 and 15 is really, really common. Foundations or building corners, building locations, foundation corners, pretty typical 10-foot offset to a building corner. If they have a really deep foundation and they need to step that wall back, you might be going 20 feet, but the contractor needs it to be close enough as well to establish batter boards relatively convenient too. So I think you're going to find 10 foot to be the most common request for foundation offsets. Whatever distance is used, you have to stay consistent, and the book addresses this. Every boss you have is going to address this. Every contractor is going to address this. You can't go mixing up your offset distances on a job site. Maybe there's a big rock or a boulder or something in the way at 3 foot for that top back of curb, and you say, well, I'm just going to kick it back a little, and at this one particular station I'm going to give it a 4-foot offset. You can't do that because you're going to introduce a potential for a big error. I know it doesn't sound like somebody wouldn't catch it, but people get in tunnel vision. People know that they're looking for 10-foot offsets for every building, and if you throw a wacky 15 there at them and you don't really make that known, an error is going to happen, and you don't want to be the cause of that error, something that can be so avoidable. So stay consistent with your offset distances. The last thing I want to talk about is a concept with regards to stakeout that the book talks about, and it's backsite length. And you're going to hear people talk about this a lot when you work with total stations, and especially people that have been doing this for years. They always talk about use a long backsite in any measurement, but especially for stakeout. And here's why. If we have 3 control points, or 2 control points here, an instrument location and a backsite location again, and a point that we want to stake out. So there's our backsite line, and there's our foresight line. We have to turn that angle, right? Well, when we sight on our backsite, there's a little bit of uncertainty. This is the random error that we're so used to talking about now. The sighting error. It could be a limitation of the equipment, or it's just the limitation of your abilities to sight perfectly with that crosshair on that target. But there's going to be a little bit of angular error, a tolerance. You don't know if it's going to be a little left or a little right, but there's a tolerance window there. generally that tolerance window is small enough that we can live with it. On a modern total station, the angular accuracies are typically 5 angular seconds or less, and we can definitely live with that on a construction stakeout job. So when we turn our angle to our foresight, that same tolerance window gets projected over there. And if our foresight distance is shorter than our backsight distance, that proportion, that tolerance window is proportionately smaller. So if we could live with the error over here at, say, 100 feet away, we're definitely going to live with that error over here at 40 feet away. The longer the backsight you have, the less tolerance error or random error you're going to be introducing to the points that you stake out. But what if we had a point really far away? All right, we're going to try and stake out something that's 5 times as far away as our backsight point. Well, that tolerance window gets proportionally extended out there as well. And at some point, you start to lose the confidence that you're getting that point in the ground exactly where you want it to be. And this kind of error is avoided if your backsight is a lot longer. So that's kind of just a general rule of thumb that you're going to hear people talk about.